Okay, so here we go. Okay, so I think we're starting with 11 here. It asks for, I believe that's where we're starting anyway. That's where we started the other classes. List three properties of ionic compounds and molecular compounds. I can hear you guys. Okay, Carter. Okay, here we go. Can you guys? No, we're moving on. You can have a class discussion after. Okay, okay, here we go. Number 11, three properties of ionic and molecular compounds that differ. And we talked about this yesterday, so obviously, again, kind of important for us. What would we say about ionic versus molecular? What are some differences between those? And we're looking for properties, but you can give me a few things here, and we'll talk about that. But what are three differences or three properties that are going to differ here? Somebody? Yeah, Carter? Okay. Yeah, I know. I hear you. And molecular is two nonmetals, yes? Okay. So that's fine. That's a good place to start for sure. We know that ionic, I think we talked about this yesterday, big difference in electronegativity, therefore transfer of electrons. Molecular compounds, not a big difference in electronegativity, therefore we're sharing, sometimes equally, sometimes not, just kind of depends. So we can put those down. We're kind of looking for a little bit more of lesson 16 properties. So there's nothing wrong with putting that down, absolutely. But let's think about some properties. How would we tell the difference between ionic and molecular? What are some things we could do? What are some things we could uh, say about their differences here? Somebody else? Jackson? Perfect. So melting points or boiling points are very high. Molecular, low in comparison, right? So we talked about that quite a bit here in the last few days. That's a great place to start. What else? Great. Yeah, absolutely. Definitely want to talk about melting and boiling points. That was kind of the other part. What else? Anybody else? Uh, Owen, you have your hand up. When it's what? Sorry. Yeah, exactly. So conductivity is another great one to talk about. Absolutely. And again, you said this. I just want to reaffirm this here. If we're going to talk about solids, this is not a difference here, right? These are probably very, very little or not conductive for both of these. Molecular should never conduct electricity or conductivity, but definitely not molecular is not. The beauty part about this is if we melt them, right, we not only do we find out the melting points, we also find out the how conductive they now become. In liquid form, these are very good, or very, well, I should say, but very good, I guess. And these are still not. Okay, so remember that because that's going to be important for us. Okay, that's definitely another great way, and that kind of ties in. That right there ties into, I guess, the melting point there. Yeah. Uh, what else? There's one more thing that we talked about in lesson 16 that would help us kind of determine a difference there. What's the other thing that I'm thinking of here? Anyone? Brad, you want to give it a shot? Yep, that's absolutely true. Yeah, definitely. But that comes when we say that stuff, that it's not wrong. I'm not saying it's good. Those are the same things as saying high melting points and low melting points. Okay, I would kind of equate those to be the same because that's really what it comes down to as far as how well they stick together. One more thing. Anyone? Jaron? High stress, you said? Yeah. So, yeah, exactly. When you stress or hammer them, okay, uh, these charges, these like charges will start to build up and, oops, that's not, there we go. And they will break in a smooth plane, yes? So they tend to break or cleave, they say, in a smooth plane. These just in general are just very soft in nature. Okay, so that's another good way to tell the difference between those two. And if you're going to talk about the differences between these at some point, make sure you state that for those compounds. What do they do? If we're going to do a stress test on a metal, for example, I didn't actually mention this in the other classes. Remember, they dent, right? Because electrons are free to slide over each other, et cetera, et cetera. Okay. All right, moving on. Putter, just sit still. Um, 15, I guess. 15, I'm just going to read these out to you. 16, I'll write the formulas, but 15, I'm just going to read them out to you here. You definitely need to know, I don't know exactly which questions you're going to get here, but you definitely need to know how to name compounds. They're going to give you like 3 or 4 of those to start off with, just to kind of get you in the groove, or maybe 2 anyway, just to kind of, get you in the groove of the test kind of thing. So naming these would be what? 15A is nickel 2 oxide. Don't forget the 2 part. Nickel 2 oxide, Roman numerals. Sulfur trioxide for B, sulfur trioxide. C is potassium carbonate. D is tetraphosphorus deca oxide. E is sodium. And then the PO5 part, remember that's perphosphate. PO4 is phosphate. PO5 is, or what did I say? PO4 is phosphate. PO5 would be perphosphate. Okay, we have to put that little prefix on the beginning. F is ammonium, NH4. Ammonium, and then HCO3 minus is hydrogen carbonate. Those are both polyatomic ions in the list there, of course, that you have. So ammonium hydrogen carbonate. G is dinitrogen monoxide. Dinitrogen monoxide. H is sodium hypochlorite. OCl is actually, again, in the top left there. Sometimes they write it as OCl or ClO, depends. But OCl there, that's a 1 minus. That's hypochlorite, sodium hypochlorite. And silicon dioxide would be the last one there. Okay, if there's any questions, let me know. 16, we're going to go with mercury 2. So 2 plus. Sulfide, don't forget, we have to remember those charges. Remember, they're not on your periodic table unless you wrote them in there. But S is a 2 minus. Okay, don't forget that. O is a 2 minus. Nitrogen is a 3 minus. That's what happens when you combine them with metals, of course. So in this case, mercury 2 plus, S is a 2 minus, so we swap, drop, reduce for those ones. B is calcium hydroxide, which looks a little something like this here. Calcium's a 2 plus, hydroxide's a 1 minus. C, we got chlorine gas. Don't forget chlorine gas. Cl2, right? I have no very clever friends, people stupid, or Hofbrinkel, yes? So we got to remember that. Cl2, chlorine. D is sulfur dioxide, SO2. E, I ran out of room there, but that's okay. E is cesium fluoride, so 1 plus 1 minus. F, ammonium. And this is nitrite. So remember, NO3 is nitrate. Nitrite would be NO2. Okay. And then if we want one less than that, that'd be hyponitrite. Right? NO would just be hyponitrite. Manganese 4. Gave you these ones for a reason because, of course, we have to remember that 4 plus here, oxide's a 2 minus, swap and drop, and we get MnO2. Okay, swap, drop, reduce. Don't forget to reduce. H. Where are we here? Lead 4, sulfite. Buy the bike racks after school. 4 plus 2 minus 2. Okay, swap, drop, reduce. And calcium oxalate. I don't even know if I want to say this joke. Because you're not going to laugh anyway. 2 plus 2 minus swap, drop, reduce. Yes? Good? Yes? Give me a nod. Yes. Careful the last one. There's a potential for a lot of mistakes there. Uh-oh. CC. Uh-oh. See? Told ya. All right. No, I don't think so. All right. Who's going to tell me difference between what's intramolecular forces? What are we talking about there? I'm just going to have to speak up. What does that mean for us? Intra. Who's there? Let's see. I don't want to pick. I can't. Oh, let's see. What's intra? I'm going to go with, actually, I can't even see you, but Josh. No, not Josh. Brandon. Brandon. Are you still awake? You didn't answer that question. Nathan. Perfect. So just a quick reminder. Yeah, I don't even need to really say that again, but this would be an example of intra. It holds that one molecule together. It's really just a fancy way of saying covalent bonding. Covalent bonding, remember, is not, it's decent. It's okay as far as strengths. Where they get weak here is when we start talking about between bonds, yes? So this molecule here, this intermolecular force, which of course we would say is hydrogen bonding in this case, that's substantially weaker, of course. That's between molecules. Intra is just one of those molecules, covalent bonding. Good, thank you. All right. I guess we're on to what, 20, eh? Sure. 20. It says radon gas boils at a much higher temperature Y than krypton. So what are we talking about here? Remember, we're talking about boiling and melting points. So anytime we're talking about boiling and melting points or which one's stronger, we look at our little chart. Metallic, ionic, no. Molecular, yes, these are nonmetals. Hydrogen bonding, I don't think so. Dipole, no. London forces, size and shape, right? And of course, radon's probably got a larger, well, it doesn't, of course. Radon does have a larger size. It's bigger, it's got more electrons, therefore radon is going to have apparently a much higher boiling point. Okay, so this is just due to size of electrons. Okay, size of electrons, more electrons. So that's going on there. Where are we now? Lost my place. Oh, I like this one. Again, HCl or argon. They're telling you that HCl also boils at a much higher temperature. Why? Why does HCl boil at much higher temperature? Anyone? Santi? You betcha. The good old dip, yeah. And this would be just London, right? This is just one atom, so we're talking about, size, shape there, but it doesn't matter at that point. Dipole, remember, is polar. Polar molecules tend to boil at higher temperatures, yes, or melt or whatever, because, of course, they're polar. They have permanent dipoles, yes? So they're always on, so we want to go with that. We don't have to get into size or anything. In fact, they told you that size was the same. They told you that for a reason. Shape, again, doesn't really matter in this case, I don't think. Dipole is going to be your winner there. So that's what we need to have for that. Okay. CH4, again, I kind of, these last two questions, or the next two, I should say, I kind of regret giving you a little bit because they're kind of silly. Having said that, we've talked about this. Remember that this bond right here, okay, they're saying, hey, what kind of, and I guess this is important for another question coming up here, but they say that bond is polar. That's true. That's a polar bond. Okay. Make sure you answer the questions. Same thing next Thursday. Make sure you're looking at the questions. This is a polar bond. That's a polar bond. That's a polar bond. Polar bond. I know they're polar because they're different in electronegativities. It just happens that those electronegativities, those polar bonds cancel each other out. So polar, 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 polar. And yes, it becomes a non-polar molecule. Okay. So remember, those polar bonds cancel out and become a non-polar molecule. Okay, and then they talk about hydrogen sulfide. I'll just draw that real quick here. Looks a little something like this here, of course. They're just saying what is a bent molecule, what it kind of explains that. And again, we have these lone pairs here and then these bonds here, but it forces that into that bent shape where we have S here and then the H is here kind of thing. That's just tetrahedral bent. We know that AX2E2 kind of thing is what's going on there. Okay. Okay, moving on here. Almost, this won't take too much longer here. Oh, which is also important here. Just a little review. We haven't talked about this for a while, so I would understand if you forgot. But this is CH4. This is tetrahedral. These are all bonding pairs. So we know that the bond angle here is 109.5. If we move on to the next example of tetrahedral, if you remember when we had our, we did our Vesper shapes and all that, we get this here. But remember, this bond angle here shrinks down to 107.3 because what do lone pairs do? They, what's the word there that I'm looking for? Somebody. Yeah, they repel more, right? So they push more on the bonds around them, and as a result, we shrink that bond angle a little bit. Okay, so they repel, and that's never more true than when we get to water, or for that matter, H2S or something like that. This is shrunk again, 104.5, and it shrinks because again we have two lone pairs now that are now pushing on those bonds away from them. Okay, they're repelling more. And remember that lone pairs repel most, bonding pairs the least. Well, they don't push as hard, right? So, all right, good. If there's any questions, just put up your hand there, and if I see you, I'll answer them. 25, I guess. We got CO2 is a gas. They tell you that. And in case, these states here are kind of important, right? I mean, that's not really the question here, but obviously when you look at these two states, one says CO2 gas, one says CS2 liquid. I already know that this one's the stronger one, yes? And I know that because at room temperature, the other one's a gas, this one's still a liquid, it hasn't boiled yet. So out of these two, I know that's stronger, and they already tell you that, of course, so that's not really the question. They're just asking you why. And of course, if you're ever in doubt, we draw them out. That rhymes. I just came up with that. If you're in doubt, draw it out, okay? But we're going to find out, of course, they're going to have the same shape. They're both linear. They're both AX2, 180 bond angles, both nonpolar, London forces, size, and shape. And size, of course, is the difference here, okay? This has got a larger size, more electrons, more temporary bonds. More temporary bonds, the better the London force, the better they stick together, the harder it is for them to boil or melt. In this case, it hasn't actually boiled yet. All right. Good. Next, I'm just having a little trouble here. Just give me a sec. There we go. I gotta do this. No, no, nope, nope. Well, that's not working. Let's try this again. All right, I have to use different. There we go. Okay. Next, we have, what do we have here? Oh, yeah, two factors. You guys know this. London forces. When we say London forces, you're going to think what? What are the two things? Yell it out, somebody. Thank you. Size and shape. And if you're, it's fine to put those two things down, but you also have to remember, and I know you know this, but we have to still state what about size and shape, right? So size, you want to put here more electrons is greater London force or something. Greater London force, and a shape, of course, linear is the best, okay, or better. All right. So we definitely want to have those two parts as part of that as well. Good. Okay. Questions, anyone there? Just make sure you put that as well. Just make sure we understand what. Don't just say size and shape, because we don't. People don't really know what size and shape, what that means. So, all right. Well, again, let's talk about number 40 next. 40A. Calcium chloride. What kind? Your options are mostly ionic, or basically ionic, I guess, roughly. Polar covalent, non-polar covalent, and metallic. Now, again, read the question closely. This is important, super important. It says, describe the nature of the chemical bonds. So what kind of bonds do we have in calcium chloride? Somebody yell it out for me, please. Ionic. Thank you. That's great. Great. Those would be ionic, yes. Again, you'd probably want to double check electronegativity there, but I'm pretty sure that's probably ionic. Metal, non-metal, we're probably okay with that. In most cases, if that's what we're doing, I'm going to give you the ionic compound. I'm not going to try. Remember the other day we talked about SBH3, and we said, well, how are you going to draw that? Ionically or sharing electrons? And we came out to be sharing electrons, even though it's a metal, because the electronegativity difference wasn't great. So. All right, CO2. What kind of bonds do we have in CO2? Who wants to answer this one? CO2. What kind of bonds do we have? Got to be careful on this one. What do you think, Brad? Polar covalent. Yes, good answer. I know. I heard you, but I heard what I wanted to hear. Polar. Why are they polar? They're polar bonds, guys. We have to remember this. Okay. This right here, that's the bond. That's the bond. Those are polar. This is a polar bond. I know that because this is 2.6 and 3.4 and 3.4. This bond right here, that's polar. Okay, electrons are getting pulled that way. That's a polar bond. Now, if the question was which of these molecules are polar or non-polar, then you'd say, yeah, that molecule's non-polar, but it's got polar bonds. They're asking about the bonds. Don't make that mistake. Make sure you answer the questions. Polar bonds. Okay. What's next here? Brass. Oh, brass. Yeah. Mixture of what is it here? Copper and zinc. What kind of bonds do we have here? What do you think? Oh, I want to pick on somebody else. I'd pick on Sachi, but this is too easy. I don't want to pick on her. Who am I going to pick on? I don't know. Wasn't answered yet. Anyone? Anyone want to take a stab? Olivia, maybe? Metallic. Yes. Metallic metals, right? We got some metals there, so metallic. See, this microphone thing works out pretty well, doesn't it? Hey, I don't think we need to get it fixed. It's working great. Metallic, because we have two metals, right? Whether it's one metal or two metals, we're going to go with metallic. Remember, positive ions in a sea of delocalized electrons. Yes. Who's got their hand up? Is that Dave? I don't know. Can you? Sure. All right. And lastly here, D, ozone. Ozone. So O to O to O. That would be what? Let's see. Who answered the other question here? I forget now. Oh, geez, I forget. I don't know. Charlie? Charlie, look up. Charlie, look up. What would it be? Charlie, look up, Charlie. Ah, there we go. Nonpolar. So we got O to O to O, right? Or I don't know what that actually. To be honest, I'm going to be quick. I have an idea, but I don't. I'm not going to draw that because I probably will butcher it. But O to O to O. So if you think about what is it, 3.4, 3.4, 3.4, those are all going to share electrons equally. Yes. Okay. No difference in electronegativities there. So we'd have nonpolar bonds. Again, even if you just went O to O, those two would cancel each other out. Okay. All right. Good. Perfect. You guys are doing awesome. Two more questions, and I'll leave you alone for the day here. 43. I guess I'm going to actually want to speed this up just a little bit here. Now, this is super important. All right. You should, and I hate to say this, I always hate this, but you should know what we're doing here. And you should know basically what they want you to do here is look at these bond between N and H and tell me, okay, if you're going to slap some partial negatives and partial positives on these two atoms, the polarity, okay, what would you be, which one is the partial negative, which one's the partial positive? We need to know that. And again, it comes down to electronegativity. So 3.0 and 2.2, and actually electrons would be pulled this way, yes, because that's the higher electronegative atom. By the way, we can even talk about the difference. That's not a bad thing either. That's actually the next question. That's a 0.8 difference. So this would be your partial negative end, partial positive, yes, and you need to know that. The partial negative end, of course, is the higher electronegative atom. The number that's higher is the negative end, okay? All right, good. B, F, and N here. And again, this is 4.0, this is 3.0. They're going to get pulled this way. 1.0 is the difference. Again, partial negative, partial positive. That'll show up here in a second. There we go. Partial negative, partial positive. Okay, good. Make sure you're able to do that. That's super important. ICL, and I'm going to have to remember this. That's 2.7 and 3.2, I think. Well, the numbers are right. Or sorry, the partial negative, partial positive would go out there and there. I think it's 2.7 and 3.2. I kind of forgotten already, even though I've done this three times today here. All right, good. That's definitely super important that we do that. Okay. All right. Next. Almost last one. Well, no, that is it. But I'm going to do one more with you real quick here. Let's do 44A. And 44A says, let's arrange the following sets of pairs in increasing polarity. So what they mean there is basically, let's do like difference in electronegativities, smallest to largest kind of thing. So if we look at CLF again, partial negative, partial positive, 4.0, 3.2, that's a 0.8 difference. Okay. That has probably, that's actually fairly large, not too bad, right? Difference in electronegativity. BR and CL, that's 3.2. BR is what, 3, I think? Yeah, that's right, eh? Somebody help me in there, 3? Yeah, okay. So that's a 0.2 difference. That's the negative end. That's not a big difference, by the way. However, there is a difference, okay? And so that difference is 0.2, but not a big difference there. I would say for the most part, I would almost venture a guess that those electrons are probably being almost very, very, very closely to being shared equally. Maybe not quite, but I think research has actually shown that they are probably shared pretty equally between the two. And what else? CLCL, like I say. And of course, that would be 0 because 3.2 and 3.2, and we'd have 0. So again, this would be the lowest polarity difference. This would be the next highest, and that would be the highest. Okay, and then maybe we'd throw an ionic compound into there somewhere, and of course that would be number 4. That would be the highest difference in electronegativity. It's the highest because, and then that's how electrons are transferred from one to another, right? So, okay. Does anybody, we got a few minutes here, 15, 20, I guess, but I know you guys, I'll let you guys work for the rest of the class here, and that's fine. But before I go, does anybody want me to do any of the questions farther on here that you want me to answer here? If you're working on them and you're struggling. Yeah, Carter, which one? Okay, I heard 57. B? Oh, E is in echo? Okay, E. All right. This one. Just tell me if it's this one, Carter. That one? Okay, good enough. Yeah, we can definitely do that. So remember, these are polyatomic ions now, right? We have this negative sign here. So there is a way that we have to draw these polyatomic ions. We're going to add up electrons, okay? Because this molecule gets fairly complex here. And remember, this -1 is important to us because that -1 tells us that, hey, this molecule, if it was just HCO3, we might not have enough electrons, but that -1 charge there tells us we've gained one. So we add up electrons. Remember, anytime you get a charge, so a charge up here, we are going to make sure that we add up electrons. Okay, we had a quiz on this. It was quite a while ago, though. So that's 1. Remember, in this case, we're just adding up valence electrons because those are the only ones that we use for bonding. Okay, and this is 6, 6, and 6. There's 3 of them, so that's 18. And 1 more, and you'll notice that 1, like I did before for you, Carter, that's the difference there. That 1 is important because now we have, if I can add here, 24, I believe, electrons, yes, altogether. So 24 electrons, and then we need to come up with kind of what we could, this is good review actually, because we're going to probably have to draw a polyatomic ion for the test. And then we kind of start with this skeleton structure, right? Step 1 was add up all the electrons, account for the charges. 2, draw a skeleton structure. If I had to pick between H, C, and O, which one do you put in the middle, roughly? Probably C, thank you. I don't know what the deal is with the thing, C. And then you're going to, like I said, draw the skeleton structure. And we know that C usually has 4 things around it, and it does. I'm going to put the H there because I want to, and there, and there, and there. Remember, the next step now is you need to connect the outside atoms to the inside atoms. So we're going to do that with some dots here. So there's your covalent bond. There's 1, 2, 3, 4, covalent bond, 6, 7, 8. Okay. So that's used up 8 of the 24 electrons so far. Then we start going to the outside atoms. Now, we can go to H here, but H is already, I guess you could say, happy, right? He's got his 2 valence electrons stable already, so that's all good. So we don't need to worry about him. He's happy the way he is. Then we're going to go to O. Okay, well, we had 8. So here comes 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Is that enough? Yeah. Right? Is that good or no? Did I use up all 24 or no, or did I lose track? No, I think I used the 24, didn't I? 8, 8, that's 16, 17, 18, 19, 20, 21, 22, 23, 24. Is that how many I had to use, right? 24. Yeah. Yeah, exactly. So now we're going to have to manipulate this somehow, right? So we might actually have to, in this case, we might actually have to do this a little differently. This is actually a little trickier than I thought here. Usually with this one, I'm just going to back this up for a second here. Usually with this one, I would probably have, for this diagram here, I'm going to get rid of those. We would probably do, for the most part, I guess this is a little trickier than what I thought here. We usually do this one, yes? Carbonate. And then we'd go, we do this, and then we put those 2 electrons right here, yeah? So then we'd have this kind of thing. We'd move a pair in, if that makes sense. We make a double bond there, we'd have carbonate. Good? I'm going to fix it right away here, but is that okay? That's probably the one that I would give you. I probably wouldn't give you the other one. And then of course, when we do that, I'm just going to finish this off here because I don't like leaving it like that for a second here. But C, we'd have a double bond O. This is what we'd end up with, and an O and an O here. Anytime we're drawing polyatomic ions, remember, polyatomic ions, make sure you put brackets here, yes? And actually this one, I think carbonate would have a 2- charge. So don't forget the brackets and the charge, yeah? Okay. Now this one though, so we can do that. We'll do another one tomorrow, I think. The other one tomorrow is, where'd it go here? What's beside that one? Oh, right there, NO3 1-. That's probably a better one to draw anyway. I'm not trying to cop out on you, but that's probably a better one. So we'll do that again tomorrow with nitrate, for example. If you're going to draw HCO3 again, it's a 1-, I think, yeah. So I said 24 electrons. Now this is where you'd have to get a little bit fancy here, and you know, again, maybe this skeleton structure is not going to work for us, because we're only going to end up with 6 around that oxygen there. So maybe we've got to look at something different, right? Maybe perhaps we need to, in that case, look at maybe putting the H over here or something, and getting rid of this one here, okay? And again, connecting them all together. 1, 2, 3, 4, 5, 6, 7, 8, but maybe looking at doing something different. Now, the issue might become here. We need a pair of electrons there. I guess that's 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Maybe something like that. Carbon's not good enough though. So in this case here, because carbon doesn't have 8, now I would probably recommend taking like this pair here and shoving it into there to make a double bond there, okay? And like I said, that's kind of a little tricky on that one for sure. I wouldn't give you anything like that. I probably shouldn't have given that to you on the questions, but I did. So, but that would probably take care of that issue there. So we'd have C double bond O, single bond O, and then O, you know, and it'd probably look a little something like this here, okay? Something along that line there, okay? That's kind of a tricky one for sure, so don't worry about that too much, all right? Good. Okay. Any other questions before we wrap it up for the day? Okay. All right. Okay, well, all I'm going to say is just make sure you guys finish those questions off. Make sure you try them, right? We need to make sure we're practicing, especially the drawings. You know how big a deal that is, right? Because that allows us to predict if it's ionic, metallic, molecular, hydrogen bonding, dipole, dipole, and force side shape, and allows us to slot them into the right spots. Okay, so that's a pretty big deal. But yeah, make sure those questions are done for tomorrow. We'll see if I'm there tomorrow or not. I don't know. I can't tell. And we'll go from there. Okay. Okay.